In this video, we start our discussion on Chapter 19. In Chapter 18, we went through acid-base equilibria and introduced the ideas of weak acids and weak bases and chemical equilibria. Now, in this chapter, we're going to look at more advanced concepts relating to acid-base equilibria, but we'll also add in discussion of salt solubility and ionic compounds and complex ions. In our first video, we're going to go through acid-base buffers, and we'll start looking at acid-base titration curves going through strong acid, strong base titrations. Acid-base buffers are extremely important substances. They're ubiquitous. They're present in biological systems, in the environment. They're very important for industrial applications, and you see them all over the place. Acid-base buffers lessen the impact on pH of addition of acid or base to a system. An acid-base buffer consists of a conjugate acid-base pair where both species, that is, the acid and its conjugate base, are present in appreciable quantities. Acid-base buffers are a solution of a weak acid and its conjugate weak base. Here we can see the effect of a buffer. Now, in this first image, we see a 100 milliliter sample of dilute hydrochloric acid is adjusted to pH 5, and that's shown on the left picture. So we have 100 milliliters of water, and we add a very small amount of dilute hydrochloric acid, strong acid, and the pH goes down to 5.00. Now, if we add 1 milliliter of strong acid to this system, the pH drops down to 2. So there's a huge change. Or if we add 1 milliliter of strong base, the pH jumps all the way up to 12. So you can see each pH unit corresponds to a change by a factor of 10 in the hydrogen ion concentration. So we're seeing many orders of magnitude change in the pH of a solution when it is not buffered. Now we can contrast this with a buffered solution. We start off with a 100 milliliter sample of acetate buffer, which is going to be a mixture of acetic acid plus sodium acetate. And we can adjust that pH to 5.00 as shown on the left-hand side. Now we can do the same thing we did in the upper panel. We can add strong acid. So if we add 1 milliliter of strong acid, we see that the pH does drop, but rather than going from 5 down to 2, the pH drops down from 5 down to only 4.98. And correspondingly, if we add 1 milliliter of strong base, the pH doesn't go all the way up to 12, it only goes up to 5.02. So the buffer modulates pH change by very large amounts. The way buffers work can be visualized through the common ion effect. We talked about that previously, so let's look at the acetic acid case. So if we have acetic acid and we put it into water, it dissociates slightly. So the acetic acid reacts with water to form acetate and the hydronium ion. Now, if sodium acetate is added to this solution, this dissolves completely, the sodium comes off, and we have acetate. Now, this is a common ion effect. As you add acid to the reaction that's shown here, that's going to push the equilibrium towards the left, following Le Chatelier's principle. So acetate is the common ion to both solutions. What this does is adding the acetate reduces the amount of dissociation of the acetic acid that was initially in the solution. So you can see that the acetic acid by itself will dissociate a little bit, but if we add acid, it pushes the equilibrium back towards the left. You could actually do the same thing if you took a pure solution of sodium acetate. That would be slightly basic. Now, if we added acetic acid to that, that would push its equilibrium back towards the acetate. But sticking with the acetic acid example, Here we have a table that shows the effect of added acetate ion on the fraction of dissociation of acetic acid. So in this table, in the first column, we see the initial amount of acetic acid we add to solution. So we've got initially it's 0.1 molar for all 4 examples. On our first row, we've added no acetate. If we just throw pure acetic acid in solution and its 0.1 molar concentration, the extent of dissociation is approximately 1.3%. The hydronium ion concentration is 1.3 times 10 to the minus 3 molar, and so the pH of the solution is 2.89. In our next row, we have our 0.1 molar acetic acid, but now we add half as much acetate to the solution, 0.05 molar. Now we see that the percent dissociation drops down by more than an order of magnitude to 0.036%. The hydronium ion concentration is much smaller. It's 3.6 by 10 to the minus 5 molar, and the pH is 4.44. Now, if we have equal amounts of acetic acid and acetate, we see that the percent dissociation of the acetic acid is now 2 orders of magnitude down from the pure acetic acid case at 0.018%. And in this case, the pH is 4.74. Finally, if we add extra acetate in the fourth row, we start off with 0.1 molar acetic acid, we add 0.15 molar acetate. You can see the percent dissociation drops a little bit further, and the pH increases slightly to 4.92. But in both cases, we see that all 3 cases, we see the percent dissociation of acetic acid decreases as the acetate concentration increases. Therefore, the common ion A- suppresses dissociation of HA. And likewise, HA suppresses the hydrolysis of A-. So they work to counterbalance one another. When you have a weak acid and its corresponding conjugate weak base, they serve as reservoirs, suppressing the dissociation of their counterpart. Next, let's look at the relative concentrations of buffer components. So we continue looking at our acetic acid acetate example, and here we show the equilibrium constant. So the equilibrium constant, the acid dissociation constant Ka, is equal to the acetate concentration times the hydronium concentration divided by the acetic acid concentration. And we can rearrange this to get the hydronium concentration, which is ultimately what we'll want later on, and that will be equal to the acid dissociation constant multiplied by the concentration of acetic acid divided by the concentration of acetate. Since Ka is a constant, then the hydronium ion concentration depends on the ratio of the buffer components, that is, acetate concentration and the acetic acid concentration. If the acid concentration divided by the conjugate base concentration increases, the hydronium ion concentration increases. If, however, the acid concentration divided by the weak base concentration decreases, then the hydronium ion concentration will correspondingly decrease. Now let's see what happens when we add a strong acid to a buffer. So we know that adding strong acids to buffers, a buffer suppresses the change in pH relative to what pure water would do. So if we add a small amount of acid to a buffer, the hydronium ion reacts with an equal amount of the acetate ion, the base component of our buffer, and then it forms more acetic acid. So the acetate ion acts as sort of a buffer or a reservoir to absorb any strong acid that is added. The acetate concentration will go down by the amount of acid that we've added, and the acetic acid will go up by that amount, which will increase the buffer component concentration ratio. That is, that weak acid to weak base ratio. And so the proton concentration or hydronium ion concentration will increase very slightly, and the pH will decrease a very small amount. On the other hand, we can add a strong base to a buffer. If we add a small amount of strong base to a buffer, the strong base will react with an equal amount of the acetic acid, the acid component of our buffer, and it will form a little bit more acetate. Therefore, the acetic acid concentration will go down by a small amount, the acetate will go up by a corresponding amount, and that'll decrease the buffer component concentration ratio. So the hydronium ion concentration in our solution will decrease very slightly and the pH will increase very slightly. So in this case, when we've added strong base, the weak acid component of our buffer acts as a reservoir to absorb that strong base. So now we can see this graphically. In the center of this image here, we see a buffer that has equal concentrations of our weak acid and weak conjugate base. So our acetic acid and our acetate. So the acetic acid in the red bar and the acetate in the blue-gray bar. Moving towards the left, if we add strong acid, what happens is that strong acid gets absorbed in a reaction with acetate to form a little bit more acetic acid. There's no free protons to move around, so the pH can't change substantially. The pH changes by a small amount due to the change in the weak acid-weak base ratio. On the other hand, we can move to the right if we add strong base. That strong base then will react with the weak acid, slightly increasing the acetate concentration, slightly decreasing the acetic acid concentration, but not allowing any free hydroxide ions to move around in solution. So here we see how this works. Here our initial buffer ratio is our weak acid to weak base ratio is equal to X, and then we'll have a pH of Y. If we add strong acid reacts with the weak base to form a little bit of weak acid plus water. The weak acid increases, the weak base decreases, and the final ratio is greater than X, and the pH has gone down. If we add strong base on the bottom panel, we see that that strong base will react with the acetic acid or our weak acid component to form acetate. The weak acid concentration will decrease, the weak base concentration increases, and our final buffer ratio will now have decreased from the initial value, and our pH will go up slightly. We have an equation that we use very regularly, and your textbook shows an approximate expression of the what's called the Henderson-Hasselbalch equation. And so we have here, taking our acid dissociation expression for a weak acid, we see Ka is equal to the hydronium ion concentration times the weak base concentration divided by the weak acid concentration. And we can rearrange to get our hydronium concentration out. And then if we take logs of both sides of that, we have minus the log of the hydronium concentration will equal minus the log of Ka minus the log of the weak acid divided by the conjugate weak base. Taking the log of a product is just the sum of the logs. And if we put a minus in front of everything, then we end up with the pH is equal to the pKa plus the log of the base divided by the acid. This is an important equation here. There's not a star shown right now, but I'll add one to your final slide deck. This is an important equation that you will use very regularly throughout the rest of the semester. So you should have this on hand. You can, of course, always derive it yourself as was done on this slide, but you need to use this equation very regularly. So you should remember this equation. It'll make your work a lot easier. pH is equal to pKa plus the log of the concentration of the base divided by the concentration of the acid. So here we see the effect of the base to acid ratio on buffer pH. When the conjugate weak acid and weak base are equal in concentration, their ratio is 1, log of 1 is 0, therefore the pH equals the pKa. If the weak acid concentration is higher than the weak base, then our ratio is less than 1. And so we have a negative value, so our pH is less than the pKa, which makes sense. A more acid system should have a lower pH. And then if we have excess weak base, then we see that the pH is greater than the pKa. Now, I will add one thing, going back to this slide. Sometimes you can write this equivalently, pKa minus log of the acid divided by the base, if you like to write it that way. Those are mathematically equivalent expressions. So now we know how a buffer works. The next thing we're going to look at is something called buffer capacity. So if you add only a very small amount of buffer to a solution, it can respond to small amounts of added acid, but eventually you can overwhelm the buffer. The buffer capacity is the ability of a buffer to maintain the pH following addition of protons or hydroxide ions. So if we have higher concentrations of our weak acid, weak base pair, we increase our buffer capacity because we have more weak acid and weak base to react with any strong acid or base that will be added. This is one of the most important drivers of buffer capacity. The second thing that's important to buffer capacity is having the weak acid and weak base concentrations being close to one another. That means that you really want to have a buffer that has a pH near to the range that you want to maintain the pH for your system. That way you have an ability to respond to an added acid or to added base. Here we see an example of the effect of concentration on buffer capacity. There is an equation for buffer capacity. It's a fairly large equation. We're not going to cover it in this course. You will cover that if you go into Analytical Chemistry 1, we'll look at that in detail. But here we'll just look at the general trends. So here we have 4 different systems. These are all the same buffer, but we have different concentration of buffer in the solution. On the top of this figure, we have a 1 molar buffer. Next down, we have a 0.03 molar buffer, 0.1 molar buffer, and a 0.03 molar buffer. In each of these cases, we've added a small amount of base to our solution. We've added equal amounts of base to all 3 solutions. And you can see that for the upper buffer, for the 1 molar buffer, we see the smallest change. As we decrease our buffer concentration, the change becomes larger and larger. And for the smallest panel, 0.03 molar, you can see that effectively we've not properly buffered this solution because we've had a change that is almost a half a pH unit. That's a very large change. Now, in considering the ratio of weak acid and weak base to maintain a good buffer capacity, we consider something called the buffer range. The buffer range is the pH range over which a given buffer is effective at slowing down or minimizing pH changes. The buffer range is related to the ratio of the buffer components, that is, the weak acid and its conjugate weak base. The closer that ratio is to 1, the more effective the buffer is. If the concentration of one component of the buffer is 10 times the concentration of the other, or more, the buffering action will be poor. So if we have HA divided by A minus is 10, or HA divided by A minus is 0.1, then we're not in a good range. So if the log of 10 is equal to 1, or the log of 0.1 is equal to minus 1, then buffers have a usable range within plus or minus 1 pH unit of the pKa. This is how we select buffers, and we'll do this in class. We'll select the best buffer using a buffer table, and we'll pick out the one that will work best for a given pH range that we want to maintain. Now, how do we prepare a buffer? This is important. So if you're in a health sciences lab or a biomedical lab, you'll often want to make a buffer. And we do this very regularly in chemistry, chemical biology, and biochemistry labs. The first thing we have to do is to choose the conjugate acid-base pair that we're going to use for our buffer. The pKa of the weak acid should be as close as possible to the desired pH that we want to maintain. Once we have that, then we use the Henderson-Hasselbalch equation. We put in the pH that we want to maintain. We put in the pKa for our chosen conjugate acid-base pair. And then we calculate the ratio of base to acid that we need to have for this system. We make sure we have sufficient buffer capacity, and then we put in our solutions. Now, when we do this, generally your pH, when you add things, your pH will not be exactly the value you want it to be. That can be because there may be dissolved carbon dioxide in your water, stock water solution from the air, or there could be other components that provide slight impurities that can adjust the pH. So we fix the pH, adding either strong acid or strong base to very slightly move the pH right to the desired value. Then you have your buffer ready to go. Next, we're going to look at acid-base titrations. These are very important experiments and processes that are used, literally done millions of times a day all around the world. In an acid-base titration, the concentration of an acid or a base is determined by carrying out a neutralization reaction of that acid or base with a solution of either a corresponding strong base or strong acid that has a known concentration. When you carry out this reaction, the equivalence point is when the number of moles of base added equals the number of moles of hydronium ion that were originally present, or vice versa. That's the equivalence point. The equivalence point is, in some sense, for our purposes, a theoretical value. We can never know that exactly. This is what we're trying to determine. When we carry out an experiment, we observe an endpoint. An endpoint is when our instrumentation, which might be a pH meter or an auto titrator, or if we do this manually, this is when the indicator color in the solution changes. And the indicator that we select should have a color change that occurs when the pH is at the equivalence point, or as close as possible to that value. Now, each of us will have a different response or receptivity to color. Some people are very good with color changes and others have more difficulty observing color changes. This can affect the endpoint. Now, the error that we have for this system will be the endpoint minus the equivalence point. We'll start off and let's look at a strong acid-base titration. So this would be a reaction, in this case here, of a strong acid, and then we're going to add strong base to this solution. This might be a case where, we will have if the added sodium hydroxide is known in concentration, we'll call that our standard, and our unknown would be the acid concentration we're trying to determine. So when we start off, our pH is low. Now you might say, well, if we know our pH, we know what the acid concentration is. That is true, but it's known very imprecisely, because remember, a pH range covers an order of magnitude, and we may only be able to measure the pH within a precision of 0.1. And that means that you can easily have a 10% or larger error in your hydrogen ion concentration. So the reason we do titrations is to get a precise measure of concentration. In fact, titrations can be some of the most precise measurements that we can make in science. So here we see a table on the left-hand side that shows the volume of sodium hydroxide we've added to our solution, along with the pH. So you can see that since we have a strong acid, before we add any base, the pH is low. Here we have 0.1 molar hydrochloric acid. pH starts off at 1. The log of 0.1 is -1, so minus the log of the hydrogen ion concentration gives us a value of 1. As we begin adding base to this acid solution, the pH will begin going up. And you'll see that it slowly rises until we get close to the equivalence point. Since we have 40 milliliters of 0.1 molar HCl, if we're reacting it with 0.1 molar sodium hydroxide, and it's a 1-to-1 reaction, we're going to need 40 milliliters of the sodium hydroxide to have equal numbers of moles of the hydrochloric acid and the sodium hydroxide. So in this case, 40 milliliters will be our equivalence point. And we see once we reach the equivalence point or get very close to it, the pH rises up very quickly. And at the equivalence point, the pH is equal to 7 because we have equal amounts of strong acid and strong base forming pure water plus the counterions sodium and chloride, which have a very minimal effect on pH. And as we continue adding strong base, the pH continues to rise up, but eventually levels out at a higher value. Let's go through each of the steps on how we calculate what the pH of our titration solution is. You'll get a chance to do this on your ALEX homework. These are important calculations. And you will also do this in lab. Your initial pH is given by your initial hydronium ion concentration. And so we take the pH is equal to minus the log of the hydronium concentration. Once we begin adding strong base to this solution, a reaction occurs. So the pH for any point between the starting point and the equivalence point is given by the following calculation. We have our initial moles of acid, our molarity of our acid times our volume of acid. And then we have the moles of base that we've added. That is the molarity of base times the volume of base. The reaction goes to completion. And so a strong acid, strong base titration is relatively simple. The number of moles of strong acid that will remain will simply equal the moles of acid that we started off with, subtracting off the moles of base that we have added. Thus, the hydronium ion concentration will equal the moles of hydronium that remain divided by the volume of acid plus the volume of base. That gives us our concentration of the hydronium ion. And our pH is equal to minus the log of the hydronium concentration. If we wanted to do a titration curve completely, we might want to throw this equation into a spreadsheet and allow the computer to calculate it for us. Once we reach the equivalence point, as we discussed before, the pH equals 7 for a strong acid, strong base titration, regardless of our starting conditions. Now, when we get past the equivalence point, we're adding excess base. So now our pH will rise up, continue to rise up, and so we can calculate the excess hydroxide ion concentration using the calculation shown here. We can calculate the starting amounts of hydronium ion from our molarity and volume. We can calculate the moles of hydroxide we've added, which is given by its molarity times its volume. Now the hydroxide is in excess, and so the moles of hydroxide in excess is given by the moles of hydroxide, subtracting off the amount of hydronium that we started with, and therefore our hydroxide concentration is the moles of the excess hydroxide divided by the volume of acid plus the volume of base. And the pOH is given by minus the log of the OH, and then your pH can be calculated by 14, subtracting off the pOH value. Here on the next two slides, we'll do an example calculation for our 40 milliliters of 0.1 molar HCl being titrated with 0.1 molar sodium hydroxide. We calculate our initial pH, that's 0.1 molar, and we take minus the log of 0.1 to give us a value of 1. After we've added 20 milliliters of sodium hydroxide to this solution, we can see our calculation here. We calculate our initial moles of hydronium, which is 4 by 10 to the minus 3 moles. We calculate the hydroxide we've added at 20 milliliters, which is going to be 2 times 10 to the minus 3 moles of hydroxide. So now the excess hydronium will be the starting value, 4 times 10 to the minus 3, subtracting off the hydroxide which is added, 2 times 10 to the minus 3. So we get 2 times 10 to the minus 3 moles of hydronium, from which we can calculate the pH. We take this and we divide by the total volume, which is our 40 mils of acid plus 20 mils of base. And we have 0.03 molar hydronium, so our pH is 1.48. At the equivalence point, the pH is 7, as we said before, because we've added equal amounts to produce water and neutral ions, sodium and chloride. After the equivalence point, the pH is calculated as follows. For 50 milliliters of sodium hydroxide, now hydroxide is in excess. We can calculate the moles of OH added, which is 5 times 10 to the minus 3. And then we can subtract off our 4 times 10 to the minus 3 moles of acid that we started with. So we end up with 1 times 10 to the minus 3 moles of hydroxide in excess. We take that number and divide by our 40 mils of initial acid plus 50 mils of added base, and we get the concentration of hydroxide, from which we can get a pOH, and finally the pH value of 12.05. Next, we're going to look at weak acid and weak base titrations with strong acids and strong bases in our next video.